Hi everybody. This video is going to be on section 1.8. We learn a couple of special change of variables technique. Okay, so we need a couple of definitions for this section. So our first definition, a function of two variables, f of x, y, is said to be homogeneous of degree 0 so homogeneous of degree 0 if f of tx comma ty is equal to f of xy for all t greater than 0 such that tx ty is in the domain of f. Okay? Let me make this a little more clear here. Okay? So another way to look at this, so let me just rephrase what this means. So this means that if we plug in tx and ty, it's just like plugging in xy. So, i.e., f is called invariant under rescaling of the variables x and y. Okay? Because that's all we're doing. If you multiply x and y, what we're saying here is if you multiply x and y, the inputs, by any positive number, it does not matter, you end up with the original function again. So, as a further definition, guys, f is homogeneous of degree n if f of tx comma ty is equal to t to the n times f of x, y. Okay, so you could see why if n is 0, that's how you get the definition above. So what we're saying here is that f could be homogeneous of any degree, but the one that we're going to see in this section is degree 0. Okay? So how do you check that something is homogeneous of degree 0? Well, you could just plug in tx and ty and show that it works. So let's do an example really quick. So show that f of xy is equal to x squared plus 3xy minus y squared over x squared plus 4y squared. Show that that function is homogeneous of degree 0. Okay, so how would you do this? Well, you could just plug in tx and ty and show that you end up with the same function. So what would f of tx comma ty equal? Well, if you replace all the x's with tx and all the y's with ty's, you end up with the following. T squared x squared plus 3t squared xy minus t squared y squared divided by t squared x squared plus 4t squared y squared. But you'll notice that we have a t squared we can pull out of the top and out of the bottom and cancel those out. Remember, t is a positive number. It's not 0 here. So we're allowed to do that. And we end up with x squared plus 3xy plus, minus y squared over x squared plus 4y squared. And you'll notice that what we ended up with is exactly the function, right? So plugging in tx, ty gives us the function. So that's it, right? This means that f is homogeneous of degree 0. Okay. Now, I want you guys to notice something because usually we don't bother checking this condition. Usually there's an easier condition to check, or rather an alternate way. So I want you to notice something. Notice if we factor or let me not write it as factor, let me write it as divide. So notice if we divide the numerator and denominator of f of x, y by x squared, we get, well, let's see what we get. So I'm going to divide top and bottom by x squared. I end up with 1 plus 3 over y. Oh, no, sorry. I wrote that wrong. 3y over x. That's what I meant to write. 3y over x minus y over x squared over 1 plus 4 times y over x squared. And do we notice that this entire thing that I just wrote down is a function of y over x alone, right? Because notice that every single term here has a y over x in it if it has any variables at all. So this leads us to the following theorem. It turns out this is not a coincidence. This is always true. So let's write this down. Theorem. A function f of x, y is homogeneous of degree 0 if and only if it is a function of y over x alone. Okay? So you can always write it as a function of y over x. Okay? Finally, we have a new definition. Our definition is if f of x, y is homogeneous of degree 0, then dy dx equals f of xy is called a homogeneous first order differential equation. So we've taken this a little further. We're now saying that dy dx is equal to that homogeneous function, or homogeneous of degree 0 function. And so what we're saying is that if we have a differential equation that looks like this, the derivative is just that homogeneous function, then we call it a homogeneous first order differential equation. So, in other words, we know that dy dx is equal to some function of y over x, right? And so this is what we're talking about. This is called a homogeneous first order differential equation. This is an alternate way of writing it, okay? Now, it turns out that we have a nice method for solving such differential equations. Okay, this section is called change of variables because we are learning two different differential equations in this section that can be solved by doing a simple substitution. So let's go ahead and write down the steps. So steps for solving. So remember, we have the following. Let me just write this down. We have dy dx is equal to f of y over x, right? Okay, so step 1, substitute. This is the trick, okay? The trick is going to be to substitute v is equal to y over x. Now, what's important here is that we still have dy dx. So that's what we just saw is going to convert the right side of this differential equation, but we still need to convert the left side. So how do we find dy dx? Well, this means that y is equal to x times v, right? And so from this, if we take this guy and we take d dx of both sides, we end up with the following. dy dx is equal to, how do you differentiate the right side? Well, we could just use the power rule, couldn't we? Or sorry, not the power rule, the product rule. So it's going to be the derivative of the first times the second. The derivative of x is just 1, right? So it's going to be 1 times v plus x times dv dx. Okay, so step 2. Let's go ahead and call this differential equation that we started with star. So star becomes, so what's our differential equation going to become? So let me go ahead and write the right side first. It's going to become, or no, sorry, I'll write it in the order that it's there. Remember, dy dx we're going to replace with, so this is going to go here, and this, this v is going to go in here, and so we end up with v plus x dv dx is equal to f of v. So this is what we get. Now, what is nice about this? Do you guys notice that this actually becomes the following? Let me do a little scratch work here. If x dv dx is equal to f of v minus v, then don't we get the following? In other words, this is separable. Okay, so we end up with a separable thing. Okay, so what would step 3 be? Just separate and solve. And then finally, the last step, step 4, is substitute back. In other words, don't forget to replace v with y over x, right? Because you're not allowed to leave v in your final answer. Okay, so these are the 4 steps. In other words, make that substitution. Don't forget to find dy dx by using the product rule. Convert your differential equation, and then it turns into a separable differential equation that you can solve. Okay? Let's go ahead and do some examples here. Example, we're going to solve the differential equation, and it's going to be dy dx is equal to 4x plus y over x minus 4y. Now, when you see a problem like this, I recommend just right away you can divide everything by x. In this problem, you would just divide by x, right? Just divide by the largest power in the denominator. But if you divide everything by x, you're going to divide by x because you wanted to have a y over x, right? And so this is going to equal 4 plus y over x over 1 minus 4y over x, right? And I hope everybody agrees that this is equal to a function of y over x only, right? Because no other variables appeared except for y over x. And so this is how we know that it's homogeneous of degree 0, and we're also ready to do our substitution. So note that this is the differential equation is, I'll call it homogeneous. Remember, this is a homogeneous first order differential equation. Okay, so we're going to do our substitution. So let's let v be y over x, or you can also write this as y equals x times v. And then just go ahead and do your product rule. This means that dy dx is equal to v plus x dv dx. So let's go ahead and replace it, okay? So this means that we get the following. V plus x dv dx is equal to, remember, each of these now is getting replaced with a v. And so we end up with 4 plus v over 1 minus 4v. Okay, so how would we solve something like this? Well, you're going to have to move this v to the other side. So I'm going to subtract v from both sides. If you subtract v from both sides, what do we end up with? We actually get the following, right? We're going to multiply top and bottom of v over 1 by 1 minus 4v over 1 minus 4v. Remember, you need to get a common denominator here. So if you do that, you get the following. X dv dx is equal to, what do we get? We get 4 plus v minus v plus 4v squared over 1 minus 4v. And then, of course, these two cancel, so we're left with 4 plus 4v squared over 1 minus 4v. Okay. we've almost written this in separable form. Let me go ahead and do this on the next line. We're going to multiply both sides by 1 over x and also multiply both sides by the reciprocal of the right side. This gives us the following, okay? This implies that dx over x is equal to 1 minus 4v over 4 plus 4v squared dv. So notice that this is separable, so I'm just going to integrate both sides. Now, the right side is the harder one to integrate, okay? The trick on the right side is to use partial fraction decomposition. Or actually, wait, no, we don't need to do that. Sorry. I thought we might need to do that, but actually we can do this by splitting it up into two integrals. I just realized that. We can actually write this as follows. The right side, we can actually make this 1/4 times the integral of 1 over 1 plus v squared dv minus, and then if you pull out a 4, that just goes away. The 4 on top and the bottoms go away, and so we're left with v over v squared plus 1 dv. We can just integrate this in two separate pieces. What's the integration of the left term? This is arctan of v. What about the right one? Well, if we do a u sub, u is equal to v squared plus 1. So du is equal to 2v dv, or 1/2 du is equal to v dv. So what do we end up with? This is equal to, what is that? It becomes the integral of, we're going to pull the 1/2 out, so it's minus 1/2, and then we just end up with 1 over u du. And so it's going to be minus 1/2 natural log of u. But of course, replace u back with v squared plus 1, and of course that's positive, so we don't need to worry about the absolute value. We get the following. It becomes minus 1/2 the natural log of v squared plus 1. What do we get on the left? Well, this guy just is easy to integrate. This just becomes the natural log of the absolute value of x. Okay. So what now? Well, replace v back with y over x. So everywhere you see a v, you're going to replace it back with y over x, and we get the following as our answer. We get natural log of x is equal to 1/4 arctan of y over x minus 1/2 the natural log of y squared over x squared plus 1. And by the way, guys, all of this has a plus c. You can write the plus c on either side. So I'm just going to write it on the right side. If you write the plus c on the left side, that's totally okay also. Just understand that your plus c and someone else's plus c are just going to be negatives of each other, right? But these are arbitrary constants. So this is how you would write your solution. Okay. Let's go ahead and try another example, okay? This time we're going to do some orthogonal trajectories. So let's find the equation of the orthogonal trajectories to the family The family is x squared plus y squared minus 2cx is equal to 0. Okay. Remember, with these problems, it's always good to solve for c because you're going to be using that in the later part of your question. So this is what I would start by doing. If you were to solve for c, that means you have to move the right side over and then divide. You end up with getting that c is equal to x squared plus y squared over 2x, right? So this is what we get. So remember, for orthogonal trajectory problems, we are not given a differential equation. So we need to create one, and you do that by taking the derivative with respect to x. So if we take this, and we take the derivative with respect to x of both sides, we get the following. We end up with dy dx is equal to, so we end up with 2x plus 2y times dy dx minus 2c is equal to 0. Okay, so this is what we get, and if we then do some algebra to get dy dx by itself, we end up with the following. Dy dx is equal to c minus x over y, but we already have c right here, so I'm going to bring it back, and we end up with the following. X squared plus y squared over 2x minus x all over y, or if we multiply top and bottom by 2x to clear out the common denominator, we end up with the following. This is equal to x squared plus y squared minus 2x squared over 2xy, but combine the like terms at the top, and we end up with y squared minus x squared over 2xy. So let me go to the next page and just write this in a new line. We have dy dx is equal to 2xy over x squared minus y squared. So what do we notice? This guy is homogeneous of degree 0. Okay? How do we know that? Well, we can divide everything by x squared, by x, and sorry, I just realized I skipped a step. We're not here yet. This is not what we get for dy dx. What we actually get for dy dx from the last page was y squared minus x squared over 2xy. Okay? So remember, this is our slope. So what would the orthogonal trajectories be? The orthogonal trajectories are going to be the negative reciprocal of those terms. And so this is where we get, if you multiply that guy by negative and do the reciprocal, we end up with 2xy over x squared minus y squared. Sorry, this is what I wrote down earlier. But remember, this, we get the negative reciprocal. Okay, so this is the differential equation that we want to solve, and this is actually homogeneous of degree 0, and we can figure that out by dividing by x squared, top and bottom. And we end up with the following. dy dx is equal to 2 times y over x over 1 minus y over x squared. Okay, so homogeneous of degree 0. Okay, so we're going to do our substitution like last time. Okay, so remember v is equal to y over x. And also remember, by doing that whole product rule thing like we did last time, we know that dy dx is equal to v plus x dv dx. And so our differential equation becomes v plus x dv dx is equal to 2v over 1 minus v squared. Okay. So if we move the v to the other side and we do a little bit of algebra, we get the following. We get, let me do that over here actually. After some algebra, we get x dv dx is equal to, when we subtract the v, combine denominators, all that good stuff, we end up with v plus v cubed over 1 minus v squared. Or if you do reciprocals and separate variables, you get the following. 1 minus v squared over v plus v cubed dv is equal to dx over x. Okay? From here, you integrate both sides. Integrating the left side is going to be tricky. This one we are going to need partial fraction decomposition. Okay? So let's do this on the next page here. Because if we factor that term on the bottom, it's v times 1 minus v squared, right? V times v squared plus 1. That's what I meant. V times v squared plus 1. And so this is going to equal a over v plus, let me call this a1, plus a2v plus a3 over v squared plus 1, right? Because you do need that linear term on top when you have a quadratic on the bottom and you're doing partial fractions. Okay? So from here, we're going to multiply by the LCD, and we end up with the following. 1 minus v squared is equal to a1 times v squared plus 1 plus a2v plus a3, all that times v. Or another way to look at this is, well, let me go ahead and distribute the terms here. We end up with a1 v squared plus a1 plus a2 v squared plus a3v. And if 1 minus v squared is equal to this, we create our system of equations by equating like coefficients, or the coefficients of like terms on both sides. So if we look at the v squared terms, if that's equal to that plus that, that gives us -1 is equal to a1 plus a2. And then if you look at the linear term, we end up with 0 is equal to a3. And then if we look at the constant term, we get 1 is equal to a1. So if you plug a1 into the top equation, so if you plug that in, use that in here, you end up with -1 is equal to 1 plus a2, or a2 is equal to -2. So we've got a2, we've got a1, we've got a3. So if we use all of those, we end up getting the following for our integral, okay? Remember, we were integrating both sides, and so now we end up with the integral of 1 over v minus 2v over v squared plus 1 dv. And on the right, we still have dx over x. Okay, but now we can integrate the left side. So this gives us the natural log of v minus, that's just a u sub, and when you do that, you end up with getting the natural log of v squared plus 1, very similar to the last example, is equal to the natural log of x, and then plus c. Of course, replace your v's back with y over x. We end up with the natural log of the absolute value of y over x minus the natural log of y squared over x squared plus 1 is equal to the natural log of x plus c. Okay. You know what? I should not use plus c because we already used a plus c. So c we've already used in our original problem. Remember our original problem? The family had a c in there. And so let me just change that to a different letter here. Let me use d instead. So these are the orthogonal trajectories. Okay, these are the curves that are orthogonal to the original curve. So the next type in this section, there is another type of differential equation, first order, that we're going to learn how to solve. So let's write out the definition for this one. A Bernoulli equation you see Bernoulli. Famous mathematician. Okay, a Bernoulli equation is a first order differential equation that can be written in the following form. So it's going to look like this. It's going to look very familiar to you. Oh, you know what? Let me use a lowercase. No, that's okay. Okay. You'll notice something here. This is not linear, right? Because of the y to the nth power. This is not linear. So something I should say, well, I mean, I guess it could be linear if n were 0 or 1. So what I should say here is note, if n is not 0 and n is not 1, then that means star is nonlinear. Okay. So we need to know how to solve this. Okay, our techniques from before are not going to work on this. Okay, so this is going to involve doing a substitution. So here's how it works. The first thing you're going to do, step 1, well, let me just write, or let me do this on the next line, okay? Or on the next page. So steps for solving. Step 1. And this is for the Bernoulli equation, right? So step 1 is you're going to multiply star by y to the negative n. So if you multiply both sides of the differential equation by y to the negative n, you end up with the following. Y to the negative n times dy dx plus p of x times, remember you had a y to the first power before, so if you multiply it by y to the negative n, you get y to the 1 minus n. And then the right side is just your q of x. What's the trick here? The trick is to do the following substitution. You're going to substitute a function u of x, and that's going to equal y to the 1 minus n. In other words, your u becomes this guy right here. Okay? But as always, we need to be careful because you still need the du dx. We don't have a du dx, we have a dy dx. So then what would du dx be? So from here, this means that du dx is equal to 1 minus n y to the negative n. Or isn't this the same as that? Now, why did I write that? Oh, I forgot something here because we had to differentiate the right side as well. So there's still a dy dx here, okay, when you take the derivative of that. And so this is what we get, okay? But why did I do that? Because now we realize that that is right here, okay? So we now know what to replace it with. It's going to be replaced with this. Okay, 1 over 1 minus n times du dx is equal to that. So then, what happens is, star, or you know what, let me call this star star, okay? So star star now becomes what? You end up with 1 over 1 minus n times du dx plus p of x times u is equal to q of x. Okay. Why is this good? Because this right here, we have just transformed it into a first order linear. Okay, this is a first order linear. Okay, this is very good, right? It's not in standard form, of course, so you do need to multiply both sides by this number over here. But once you do that, you're going to get yourself a first order linear differential equation. So step 3 is going to be to solve the linear first order differential equation. And of course, step 4 is to substitute back. So u, remember, is equal to y to the 1 minus n. So at the end of your problem, replace u with y to the 1 minus n. There is an important thing here. You'll notice that we actually had to divide by 1 minus n here. How do we know that we're allowed to divide by that? Well, remember, we're assuming that n is not 1, because if n were 1, we wouldn't have needed to do all this substitution, right? So if we go back to the original problem, if n is 1 here, then that means, so imagine what would happen if that was a 1. If that was a 1, then you could have moved that term to the other side and combined it with the p of x, and then it would have actually been a first order linear. So we're assuming that n is not 1. Okay. All right. So that's why we're allowed to divide by that, because we're not dividing by 0. So it's a pretty simple trick. Now, you're going to know to use this trick when you have a differential equation that looks like this, except it's got this pesky extra y to the n term in there. And so that's when you're going to know that this is your substitution. Okay? All right, so let me go ahead and do an example here. So we're going to solve the differential equation. This one's going to be dy dx plus 3 over xy is equal to 27 y to the 1/3 natural log of x. And they are telling us that x is positive. That's a given in the problem. So what do we notice here? Notice that this looks almost linear, except it's got this extra term here, right? Notice that if that term was not there, this would be a first order linear differential equation. However, that term is there, so because of that term, because it is y to the something, this whole differential equation we know is Bernoulli. So this is how we know that we're supposed to get rid of that term. So we're going to multiply everything by. So I'm going to multiply by y to the negative 1/3. You end up with y to the negative 1/3 times dy dx plus, what is this going to become? Well, you get 1 minus 1/3, that's 2/3, right? So it's going to be 3 over x, y to the 2/3, and then the last term becomes 27 natural log of x. Okay? So in this case, what you always do, remember, is you let u equal this. Just let u equal this. So let u equal y to the 2/3. So this means that du dx is equal to 2/3 y to the negative 1/3 times dy dx, or 3/2 du dx is equal to y to the negative 1/3 dy dx. So there's this. I'm going to replace that with this and replace the other guy with a u, and we end up with the following. 3/2 times du dx plus 3 over x times u is equal to 27 natural log of x. It's not in standard form though, so I am going to multiply everything by 2/3. And so let me do that on the next line. If we do that, we end up with, so let me write down what I'm doing here. I'm going to multiply this whole thing by 2/3. So we end up with du dx plus 2 over x times u is equal to 18 natural log of x. Cool. So there you go. We are now at first order linear. So how do we solve a first order linear? Remember, we need to find the integrating factor. So we're going to find the integrating factor, and remember that's going to be e to the integral of 2 over x dx, which is going to be e to the 2 natural log of x. I didn't need the absolute value because x is positive, but this is e to the natural log of x squared, which is just x squared. So I'm going to multiply this whole thing by x squared. I get x squared du dx plus 2xu is equal to 18x squared natural log of x. Okay. Now what? This whole left side, remember, this is just the derivative of u times x squared. And the right side is 18x squared ln of x dx. And I'm going to integrate both sides. So this is a separable differential equation, okay? How do you integrate this? So we end up with the following. The left side just becomes ux squared, okay? Now, what about the right side? The right side, you need to use integration by parts. So in the interest of time, I'm going to go ahead and just write down the answer. But remember, when you do integration by parts, you have to choose a u and a dv. Let me call it w and dv because we already used u for something else in this problem, right? U already means something else. So if w is equal to x squared and dv is equal to ln x dx. Oh, sorry, I got that backwards. Yeah, sorry, you would let u be the other part, okay? U would be ln of x, yeah. dv would be 18x squared dx. Anyway, I don't want to go through all the details of the integration. You guys can work that out on your own. And so we end up with the following. 6x cubed ln x minus 2x cubed plus c. Okay? So we could, at this point, we're not quite done because we need to replace our u. Remember what our u substitution was earlier, right? U was y to the 2/3. So if we replace u with y to the 2/3, we end up with y to the 2/3 times x squared is equal to 6x cubed natural log of x minus 2x cubed plus c. And this is how we write our final answer. You could divide everything by x squared if you want to, but I would just leave it alone. There's no point. Okay? Thank you very much for watching, guys. Make sure that you practice both techniques, the Bernoulli and the homogeneous differential equations. Thank you very much for watching.